So in this section, we are going to be going over the circuitry and some of the math that is behind the circuitry involved in modulating and demodulating our signals. So we are going to be going over several different types of modulators and demodulators. There are product modulators, switching modulators, and square law modulators, which all have benefits and drawbacks. And on the demodulation side, we have envelope detectors and coherent demodulators, which of course both also have benefits and drawbacks. So first off, we're going to be going over our modulation methods. First, we're going to go over our product modulator. This is one of the simplest methods to modulate a signal. It involves our message signal here being multiplied by our carrier here, which is added to our carrier multiplied by the amplitude that we want our carrier to be. Once these two terms are added, we will get our AM signal. This is a fairly simple way to modulate a signal. However, it does have a lot of drawbacks. At low powers, this is fairly easy and one of the best methods, but once we try and scale the powers up, say to 10 or 50 kilowatts, that radio stations commonly use, it is incredibly impractical to implement this in real life. Okay, our next type of modulator is going to be called the switching modulator. In this case, the carrier signal and the message signal are added together. Their sum is fed into a rectifier here. The rectifier is meant to replace negative amplitudes with zero, keeping positive amplitudes unchanged. We'll go over more of the math on the next slide, but a couple assumptions we have to make. We want to assume that the amplitude is large enough so that the diode acts as an ideal switch. So we want to say that our cut-in voltage of our diode is going to be negligible. And how we accomplish this is we make the amplitude of our carrier significantly larger than the amplitude of our message, so that the switching of our diode is almost completely controlled by our carrier term. So here you'll see our V in to our rectifier circuit. Our output is going to be V in if our input is greater than 0 and 0 otherwise. This can also be modeled by taking our input and multiplying it by P of t, which is just going to be this message signal here. P of t can be defined by this sum of cosines. On the next slide, we'll see once we distribute this, so we take our V in and multiply it by our sum, we will get a sum of these terms. We're going to have some low frequency terms here and some high frequency terms, and of course our AM modulated signal that we want here. These low frequency and high frequency terms we don't actually want. They are completely useless to our modulated signal. So we actually want to filter them out. We will do this with a bandpass filter in order to just isolate our two modulated terms here. Okay, our final type of modulator is called a square law modulator. This involves, again, feeding our input signal added to our carrier signal here. This will be fed into a nonlinear device. Again, we'll go over more of the math on the next slide. And then the output of that will be fed into a bandpass filter in order to isolate our AM modulated signal. So the output of our square law device is going to be A V in plus B V in squared. This is just going to be a device that you design. Once we sub in our input, so BC cos 2 pi FCT plus our message signal, here and here, we're going to get this big mess of terms. Once we simplify that down a bit, we're going to get these terms. In the green, we actually have our AM signal here. And then all of these other signals is going to be stuff that we don't want. This isn't going to contribute to our modulated signal, so we actually want to filter them out. There's going to be a graph on the next slide that will better illustrate this. But the green here is our modulated signal. So what was on the green last slide is going to be blue in this diagram. I apologize for that. but all we want is the modulated signal. All the other stuff here, we're going to filter out with our bandpass filter. Okay, so next we're going to cover demodulation circuits. Our most simple demodulation circuit is going to be our envelope detector. This consists of feeding our AM modulated signal into a rectifier circuit. You may have seen this in ENEL 343 and ENEL 361. How this circuit works is it will charge up when the voltage of the AM signal is less than what the capacitor is charged to. So it'll trace the signal up, and then the capacitor serves to fill in the gaps between the peaks of the message signal. Again, a figure on the next page will better illustrate this. So here in the dotted line, we have our input modulated signal. In the red, we have our ideal envelope. And in the blue, we have our actual envelope. So as you can see here, or as you might be able to infer from our circuit, on the rising edges, our circuit will closely follow what the modulated signal is outputting. But then on the falling edges, the capacitor will discharge slowly, exponentially, and it will fill in the gaps until the next peak. So, of course, there are some problems with this. This isn't a perfect reconstruction. The envelope detector is highly dependent on the RC time constant. So if the RC time constant is either too high or too low, the actual output will be either too high, as seen here, or too low. And it only approximates the message signal by adding the exponential decay between peaks, so it is not perfect. So the next modulator we're going to cover is our coherent demodulator. This is going to take our input here and multiply it again by our carrier signal. This is going to give us R of t, and mathematically it actually works out so that this becomes our input signal, removing some of the extra stuff that it gives. As you might be able to infer, this requires a local oscillator where we are demodulating our circuit. So this is a bit more complicated, a bit more expensive to implement, but it does create a much more accurate output. So this is going to be the output of our coherent demodulator. As you can see here, this is a cosine and this is a cosine here. These two multiplied together will give a cosine squared. Once we multiply this out with some trig identities, we will get our DC offset, some other stuff. This is just a shifted version on both ends here. And of course our message signal here, which is what we want. So we're going to filter that out with our bandpass filter. So we're going to get rid of this, and we'll just be left with our original message signal. So now we have covered a brief intro, the types of modulation, a more detailed analysis of amplitude modulation and the circuitry involved. Finally, we're going to cover some of the alternate amplitude modulation types. These all have benefits and drawbacks compared to our amplitude modulation from the last unit. Typically, they are more complicated than our original amplitude modulation, but they do either have a higher efficiency power-wise or are better at conserving bandwidth. So the first thing we're going to go over is our double sideband suppressed carrier modulation. This is basically when we get rid of our carrier amplitude. So our carrier amplitude AC is going to be 0. This removes the wasteful term from the power expression of the signal. However, there are some drawbacks. This does not work with the envelope detector when we are demodulating our circuit. So it does complicate our demodulation process. However, there are some drawbacks. This type of modulation will not work with our envelope detector demodulator. So it will require our coherent demodulator. This is actually 100% power efficient. So as you might remember in the last video, the normal AM setup is at best 50% efficient because you're wasting so much of your power on transmitting your carrier signal, which does not actually contain any useful information. So as you can see here in the graph, our message signal is going to be here. We're simply going to multiply it by our carrier signal, and this is going to give our double sideband suppressed carrier modulation. Next, we're going to do a brief power analysis on our double sideband. This is our traditional analysis, so we have a couple of wasteful terms here, and only the blue terms here are useful. That's all out the window. We're not going to do that. Instead, we're going to do our just regular power analysis on our signal. There's going to be no wasteful terms. So of course that's just going to be your signal squared and then doing your integral. Our next type of modulation is going to be single sideband modulation. This is very complex mathematically, so we're not going to go too much into depth on that end. But basically what it does conceptually is it only sends either the upper or lower sideband. This is much more efficient than traditional AM since it's sending half as much information. As you can see in the image here, this is our original message. However, you don't actually need to transfer both sides of the message since they are symmetrical. Instead of doing that, we're only going to transmit either the upper or the lower sidebands. This does involve reconstructing it on the other end, but we won't go too much into detail. Once we modulate it, we are going to get only the upper sideband or only the lower sidebands. This, of course, makes it much more efficient bandwidth-wise since it's only using half the bandwidth, but it does significantly complicate the process. And that's going to be the end of our videos on amplitude modulation. We have covered our types of modulation, from amplitude to frequency to some of the pulse modulation types. We've done an in-depth analysis of amplitude modulation and the circuitry involved, and we have gone over some of the alternate amplitude modulation types and their advantages and disadvantages. Thank you for watching the video, and have a good day.